Thanks, Alex. It's really a great privilege to be back at KITP and to be following these amazing experimental talks. So I'm going to provide a little bit more theory foundation, in particular for understanding the TMD cases that Jiaqi was showing us. So this talk is going to be mainly based on a paper that came out now almost a year ago with these three gentlemen. Aiden and Nisharga are both students at MIT. Nisharga is a grad fellow here. I think he's in the back of the room. And also in collaboration with their advisor, Leon. I also want to acknowledge a paper that was contemporaneous that came out around the same time by the Harvard group and corroborates many of the things that I'm going to be saying. And I also want to acknowledge now a growing list of collaborators on related topics, including our esteemed session chair. Okay, so the fractional quantum Hall effect, I don't really need to tell this audience, is one of the, I think, most amazing and well understood strongly correlated phenomena in nature. We know everything from ground state wave functions to universal transport properties. We know the excitation spectrum and their exotic features like fractional charge and statistics. And we even amazingly know some things about dynamics. We have some understanding of gaps and collective degrees of freedom at higher energies, and also instabilities to things like stripy or nematic states. But despite all of this exquisite understanding of the ordinary quantum Hall system, the physics of fractionalization seen therein has been really elusive beyond 2D electron systems and strong magnetic field, despite a great deal of effort in a wide variety of other contexts, and everything from quantum magnets to cuprates. Nevertheless, there's still a great deal about quantum Hall physics that we don't understand very well, which speaks actually to the topic of this workshop, mainly gapless things. So in particular, one family of states that we still are often confused about are composite Fermi liquid phases. So these are non-Fermi liquid states that occur in even denominator filling, which have, for example, emergent symmetries that people have been arguing over for quite a long time. We still don't understand many of their infrared properties, as the case in most non-Fermi liquid states. But also beyond that, we don't understand many aspects of quantum phase transitions between fractional quantum Hall states. In particular, they have features such as superuniversality, or at least proposed superuniversality of a sharing of critical exponents between quantum Hall transitions that we still don't understand. And even those exponents themselves, we have a hard time explaining. And also, as Jiaqi was discussing, we also have a sort of ongoing developing understanding of non-abelian states and where they come from, but that's still very much incomplete. But beyond all of this, really something that, again, as I emphasized on the previous slide, that we really need to understand better is how to find new platforms for fractionalization. And this talk will be focused on the case of narrow churn bands as discovered initially in the case of twisted molybdentelluride. Okay, as Jiaqi showed this amazing optical plot. All right, so to elaborate a bit more on this, around this time last year, due to heroic efforts of Jiaqi and the other members of Zhou Shu's group, the physics of the fractional Hall effect was discovered in a Moire system, twisted molybdentelluride at around 3.7 degrees. It was initially an optics measurement that I showed before and that Jiaqi showed, essentially measuring compressibility, but then later on in transport. Okay, and you can see also here. So if you focus on the middle, x-axis is filling, y-axis is resistivity. You see these nice plateau features at 2/3 and 3/5, and somewhat featureless resistivity down here. But if you park yourself at 2/3 and 3/5 and say sweep magnetic field, you see quite good quantization as shown over here, as well as hysteresis, which indicates spontaneous time reversal symmetry breaking, okay, as needed to have fractional quantum Hall at zero field. In addition, they can tune displacement field, effectively changing the bandwidth, and tune from the quantum Hall regime into more resistive regimes. And this is extremely exciting to me, since this is really, I think, the first clear indication of fractionalization beyond the ordinary fractional quantum Hall effect. All right, and shortly after these measurements, as Long showed us, we now saw essentially the same physics in a completely different system, which is rhombohedral pentalayer graphene. Here showing a bit more fractions and also a somewhat more featureful rho XX, where you see now clear dips in rho XX at various fractional quantum Hall fillings. Okay. Since Ashwin already discussed much of this physics at the beginning of the talk, I won't spend too much time on it, and most of the remainder of the talk is going to be focused on the TMD case. All right. So why is all of this surprising? Well, the kind of naive expectation that many of us might have is that in the absence of any explicit time reversal symmetry breaking in the form of magnetic field, we would expect some kind, an interplay of lattice effects and strong correlations to maybe give us some kind of inert charge-ordered state or Wigner crystal without topology. But these experiments really contradict that naive expectation. And as Ashwin showed us, there's an ongoing theoretical effort to really understand how topology can interplay with these kinds of effects. But instead in this talk, I'm going to take a somewhat different approach to understanding fractional quantum anomalous Hall, in particular asking a somewhat more low energy question of what are the correct effective degrees of freedom for understanding FQAH phases. All right, so what I'm going to argue to you in this talk is that the correct effective degrees of freedom are really composite fermions, something very familiar from the usual fractional quantum Hall effect. And I'm going to claim to you that the composite fermion framework explains many aspects of the fractional quantum Hall phase diagram. And one central feature of all of this is that we're going to propose an exotic, strongly interacting non-Fermi liquid state at half filling, which we're going to call the anomalous composite Fermi liquid. And I think so far experiments have been consistent with theory predictions, which I think is rather rare in general for all of us, so that's a great thing. All right, so I'll just jump into lightning review of ordinary fractional quantum Hall. As I think we all know, if I have a 2D electron system, strong magnetic field, my electrons fill Landau levels. The absence of interactions, when I fill individual Landau levels, I get quantized Hall resistivity and vanishing longitudinal resistivity. And then when I turn on Coulomb interactions, there are these amazing fractional features shown here, for example, 2/3, 2/5, 1/3, 2/7, which are also very well quantized. Okay? And the Hall conductivity can just be written here in terms of the filling. All right, and these, as I already said, were the first fractionalized phases seen in nature, have excitations with amazing fractional charge and statistics. But how do we understand where these things come from? So a natural framework for understanding quantum Hall physics is something called flux attachment. So if I take my original system of electrons in magnetic field and adiabatically attach fluxes to them, say a number m fluxes, then due to the Aharonov-Bohm phase, when I take one electron, now composite particle, around another, I'm going to see shifted statistics proportional to m. So if I attach an even number of flux quanta, I take fermions back to fermions. If I attach an odd number of flux quanta, I take fermions to composite bosons. Okay. And another important consequence of attaching flux is that the effective magnetic field felt by the composite fermion or composite particles is screened proportional to the number of fluxes that I attach, i.e. the electron density. And one additional important consequence of this is that the composite particles should be thought of as coupling to an emergent U1 Chern-Simons gauge field that essentially implements this flux attachment constraint. All right, so if I consider just the composite fermion example, I attach an even number of fluxes, it's possible to actually explain the vast majority of quantum Hall phases seen in nature. So say I attach 2 fluxes for specificity, then my composite fermions are going to feel a screened magnetic field, and say I postulate that they fill p lambda levels. Okay, so they're going to form an incompressible integer quantum Hall state now. And if I work out the corresponding filling fractions of electrons, what we'll find is this famous Jane sequence of fractional quantum Hall fillings. For example, here, the 1/3 state. And, okay, this is just fractional quantum Hall states, but I should emphasize that there are even broader aspects of the quantum Hall phase diagram which can be naturally understood in terms of composite fermions. So one example of this is what happens when I take the effective magnetic field felt by the composite fermions to 0. So this is like taking the number of Landau levels they fill to infinity. Okay, so now the filling approaches 1/2. Okay, if I just take the limit of this expression as p goes to infinity, I get 1/2. And now what happens when fermionic particles don't feel magnetic field? Well, they're going to want to form a Fermi sea, shown here. But as I told you before, they're supposed to be strongly coupled to this gauge field that implements the flux attachment. So there's actually some very strongly coupled non-Fermi liquid state, originally proposed by Halpin and Green. And we can think of this state as a parent of fractional quantum Hall, in that the whole phase diagram can sort of be thought of in terms of doping this state. Okay, we just fill Landau levels of composite fermions, get Jane states, and so on. And this isn't just a sort of vague theoretical proposal, but there are actually amazingly many properties of experiments that are consistent with this picture. So you can just see here that there's this resistive feature near nu equals 1/2, finite rho xx, and quite large rho xy, which is a consequence of this picture. But also, as Max was alluding to in his question earlier, there are many types of quantum oscillation experiments that can be done here which are consistent with the presence of a composite Fermi surface. And I'll talk a bit more about that at the end of my talk, if I have time. So the natural question then is, if the composite Fermi liquid is a parent of ordinary fractional quantum Hall, is an anomalous composite Fermi liquid the parent of fractional quantum anomalous Hall? And I'm going to answer that in the affirmative. And our strategy is going to be to start with the microscopics of twisted MOTE2. We're mainly going to focus on that case, apply numerics, and build some theory foundation from there. All right, so first, what are the basic ingredients that we're going to need for FQAH? And some of the other speakers have already touched on this. So the first thing is you need some kind of spontaneous time reversal symmetry breaking. Okay, so for example, ferromagnetism. And one sort of consequence of this, this isn't always true, but you can maybe then think of the electrons as being able to see some net pseudo-magnetic field as a result of this. The other ingredient you need is narrow Chern bands that look, in some sense of the word look, like Landau levels. Okay, and you want in particular the projected Hamiltonian to resemble in some way the lowest Landau level projected Hamiltonian. And TMD materials are sort of nice candidates for this. So they have strong spin orbit coupling, which locks spin to valley. And if you have spontaneous ferromagnetism, essentially you have all of your electrons running into a single valley. And they also have this nice layer pseudospin structure when I twist, which was already discussed by a couple of the other speakers. And this can furnish an effective magnetic field by essentially winding on the resulting Moiré lattice when I twist. Okay. I'm not going to go into a huge amount of detail on this, but we can discuss offline if you want. All right, so a little bit more detail about what the microscopic model is. So we'll take a continuum Hamiltonian, say projected in the K valley. It's written here, so this is matrix in layer space. These off-diagonal terms are interlayer tunneling. Diagonal terms are my kinetic energy. The V's are the Moiré potential. And we're going to fit this Hamiltonian to DFT from this paper. And it turns out that actually if you take this continuum model and you do an adiabatic mapping, you can actually rewrite it in some approximation as being this sort of usual P plus A squared parallel substituted Hamiltonian, in keeping with having this pseudo-magnetic field picture. And when you look then at the resulting single particle spectrum, I emphasize this for just this free theory, you get Chern -1 band shown here. All right. So now we want to look for quantum Hall, and in particular, we want to look for the composite Fermi liquid. So to do that, we need to add interactions and project into this band. Okay, but we're not going to, importantly, we're not going to assume anything about the magnetism. So we're going to keep Valley in the game. And we're going to project Coulomb interactions into this band. So really, the Hamiltonian that we're going to study, which we'll use the exact diagonalization to do, is this kinetic energy term plus this projected Coulomb part, where really all the physics is happening in this projected Coulomb matrix element here. All right? And this is really where the band topology comes in. As I already said, we're going to study this theory in exact diagonalization and look for evidence of an anomalous composite Fermi liquid. All right. So here is the actual data. I'm going to go a little bit slowly through this. So this top left panel here is telling me, first of all, y-axis is the energy, x-axis is momentum, and this top left panel is the lowest Landau level case. This is not Moiré. Okay, and you see this patterning for 16 magnetic unit cell torus of ground states here. I'm going to comment on what this right panel is in a minute. When you do the same thing for twisted MOT2, zero magnetic field, color labels are going to be for spin, what you see is the same family of ground states, importantly with spin polarization. So essentially see the magnetism popping out here. Okay. And this already is giving us pretty good evidence that we're seeing the same state. But now if we look at this right panel here, okay, so this is essentially all these discretized momenta sitting in the Brillouin zone, and I try and pattern these ground states in here, it looks like I'm filling a composite Fermi sea. You'll have to, I can't draw you arrows for all of these, but you'll have to take my word for this. Okay, and the color green here denotes overlap with single particle block states. So the green means bad overlap. Okay, so these, you have some effective Fermi C, but not of electrons, of something else. All right. Now, we can go to larger twist angles. So that's this lower right-hand corner here, and see totally different physics. Okay, it's still a metal now, spin polarized metal, where the electrons are living the edges of the Brillouin zone. Okay, and they have quite good overlap with block states. That's this red. Okay, and the top right corner here is for the 1/4 filling case. Oh, by the way, all this is at theta equals 2 degrees. Twist angle 2 degrees. So for 1/4, actually, it turns out that the matching sort of mysteriously is even better with the lowest Landau level case, even for the whole spectrum. It's very, I don't know if that will remain to larger system sizes, but that's kind of cute. All right. And all of this is consistent with numerics done by the Harvard group, which used different DFT parameters max.
So what are these overlaps that you're looking at?
These are overlaps with the single electron, like free block states.
You're taking the multi-particle wave function and doing overlap?
This is like a, so you're taking these, like individual single particle states that you're getting and looking at the overlaps with the block state. So it's, I don't remember actually the details off the top of my head of how that overlap is taken, whether it's the full many-body wave function or if you're projecting to like one of these guys. Yeah. Actually, Nisharga may be able to answer that. We can chat offline a bit later. Yeah, continue. Yeah. All right, so, so why actually expect this physics? So, I'm going to argue to you that the intuition for flux attachment is equally applicable to FQAH. One possibility for how to do this is just to naively do ordinary flux attachment. Okay, and if there's some pseudo-magnetic field in the game, you may think that that's very natural. You can do flux attachment and screen that. But to do this actually in practice is really tricky. You would need to do actual lattice flux attachment, which is an historically very hard problem. But nevertheless, we expect that the long wavelength limit is sort of consistent with the usual continuum flux attachment. Then I think you should get essentially the same long wavelength physics. So that's really the approach we're going to take in this talk. The second option is to project into the band and work out new composite particle theory attaching vortices projected into the in the non-commutative space projected into the band. This turns out to be, well, the ideal thing to do, a very hard open problem. Even in Landau levels, this is not completely solved. And the third option is to do a parton approach. This is perhaps a little bit more general than the ordinary flux attachment, and also can naturally incorporate the Moiré superlattice and other features. This is what we ultimately did in the paper. And if you're interested, you can check out the appendix of that paper in particular. All right, so I'll just tell you what the answer is. You get essentially usual composite Fermi liquid, but now seeing the underlying Moiré potential. And if I change density from half filling, okay, no magnetic field still, this is going to cause the composite fermions to feel an effective magnetic field consistent with what you might expect. All right, and you can write a Lagrangian for this. So this is the usual Halpern-Lee-Reed theory, but with two sort of major differences. One here is the presence of this Moiré potential, and the other is the presence of this AT rho bar term here, which essentially enforces the composite Fermi liquidness at zero magnetic field. If you look at its equation of motion, you see that the magnetic field felt by the composite fermions vanishes at half filling and at B equals 0. And as a result, then at half filling, composite fermions feel no magnetic field, form an anomalous composite Fermi liquid metal, and we can interpret also this rho bar as the flux, it's like the magnetic field associated with this pseudo vector potential from before. All right. So yeah, we can also generate Jane sequence states by doping away from nu equals a half in the standard way. So if we, again, dope away, composite fermions feel magnetic field. If you fill an integer number of now effective Landau levels for them, you get, again, Jane sequence states. So this leads one to expect then the most prominent observable states in FQAH will live along the Jane sequence. And this is borne out in numerics. So for example, here's for the 2/5 and 3/5 states, you see ground state degeneracy, which is consistent with the expected topological 5-fold ground state degeneracy. All right. So now I'll talk a little bit about the experiments. So what evidence for composite Fermi liquid have the experiments seen so far? So the sort of leading order thing you might look for is a large Hall angle. So you want to look for a metallic state with rho xy much bigger than rho xx. And this is certainly seen in Xiaodong's group's experiments, although it's not really as obvious that this is a metallic state from rho xx. But certainly in Long's data, this is quite visibly a metallic state that resembles composite Fermi liquid. And now it would be nice to have something a little bit more of a smoking gun for a composite Fermi surface. Okay. And the natural place to look for that is quantum oscillations. So as I already said, composite fermions undergo cyclotron orbits when you dope. And in ordinary quantum Hall, for example, if I apply a periodic electric potential, when the cyclotron orbits are commensurate with the period of that potential, so these blue lines here you can think of as the grading, you'll see resistance minima. And so this is a sample plot for gallium arsenide, very recent. You see these oscillating features. Okay, and this can be used to extract the KF composite fermions. So something really cool about the Moiré case is that you have a built-in Moiré potential. So you don't even need to apply an external electric potential. And you may still then see quantum oscillations just doping density away from nu equals a half. And in particular, what one will then find are resistance minima with periods set by the Moiré wave vector. And if you plug in experimentally realistic values for MOT2, you'd get that the period in 1 over the deviation from half filling is 2.3. So that's possibly visible. And really, I think the main impediment here is disorder really suppressing quantum oscillations. So perhaps in much cleaner samples, this will be a possibility. All right, so just to summarize, what experiments do see is an extended region of metallic behavior with rho xy much larger than rho xx, and fractional quantum anomalous Hall fractions, all consistent with Jane. So this is all giving you evidence of composite Fermi liquid. And something that's not yet really seen are these commensurability oscillations or more direct signatures of the composite Fermi surface, or something that, say, probes the non-Fermi liquidness at max.
I thought that in this material, it's the Moiré that gives you the short band. So I somehow thought that this geometric resonances somehow want some much larger period Moiré or something like that.
You mean like something in addition to the Moiré? You'll get additional resonances if you have a periodic potential on top of that.
Yes, but the original thing, how does it give you? I thought that the wave vector would just be like bigger than the. It's like some UV cutoff, right?
Right.
More band, so somehow in the.
Well, the filling is still order 1. It's still, and that's what is setting the composite fermion wave vector, right? I mean, you have the density there, which is.
Maybe we can go back here.
Yeah.
Do you have a Fermi surface?
You have a Fermi surface. Yeah.
And then the Moiré potential gives you what kind of wave vector on the Fermi surface? Is that right?
Yeah, I think that's correct. I mean, this is just the sort of usual Weiss oscillation picture.
So how big or how small is that? Compared to the size of the Fermi surface?
We have a number in the paper. I forget off the top of my head what the size of that number is.
Okay,
yeah, we can talk about this offline, yeah.
And you can, that 1 over 2.3 or that?
Yeah.
Yeah, so what exactly is that? So this should be something that's periodic
in 1 over delta n, yeah.
Which is just the same as, I mean, the fractional Hall states are also periodic.
Yes, yes.
So this is
This is
a different
a different periodicity from the,
periodicity that's much shorter.
yeah, yeah.
Is that right?
That's so there's some competition between the Shubnikov de Haas oscillations, which are giving you the dips for the Jane states, and these Weiss oscillations. So you want to always be in a regime where that period is shorter so you can actually see those. So for example, in the gallium arsenide plot here, these things are not denoting fractional quantum Hall states. And it's sort of living in close proximity to the 1/2.
Yeah, but I guess those oscillations that in this system, it's the same question that Anax has.
Yeah.
And they're also commensurate with the Moiré.
Right.
And there's just some different set of rational.
It's a different set of rational fractions, yeah.
But here it has nothing to do with the rational fractions.
That's right.
At the lambda level, it just has to do with something really geometric.
Yes, that's right.
Here it's another set of fractions.
Yeah.
Okay. But you don't know what those fractions are. You don't have it. It's not obvious what that sequence is.
Well, okay, so that sequence is given by essentially this formula. This composite fermion wave vector is set by the density at half filling. Okay, and this here is the Moiré wave vector. So from this formula, you can deduce out what the period is.
Yeah, and there should be some way to just express that just as
Yes,
like
yes. Yeah. Yeah, we have that formula in the paper.
Why undo just other fractional quantum Hall states? Like if I went to lower that temperature, would those just become?
Would you get plateaus?
Are they just the same set series?
No, it's not the same series as Jane. Yeah.
Okay, so it's just a very high p-value.
Well, no, because in the absence of the periodic potential, you wouldn't see this. You would see.
In the absence of the periodic potential, none of this physics happens.
Right.
So.
Well, I mean, if you have this, okay. I mean, if you have disorder, for example. Sure.
Is it a statement about like the energy scales of the higher t given sequence states actually, rather than existence?
Yeah, I think that may be the correct way of thinking about it.
So somehow that like the high p Jane sequence states are
can be thought of as in the presence of the lattice. Yeah, that's probably a better way of thinking about it. Yeah. 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 That makes sense. Yeah. All right. So, well, I think we're running out of time a bit, so I think can we? I only have a couple more slides. Yeah. So, yeah. I mean, actually, you know what? Why don't we start questions now, since there are many questions, and yeah, I'll. If I have time after the questions, maybe I'll talk about the slide after this Outlook slide. But yeah. Yeah.
So for the composite for the zero field composite fermions, you can still feel an external magnetic field, right?
Sure.
So my external magnetic field is effectively doping the system.
Yes.
So can I see the same, say, predicted oscillation with respect to external magnetic field, or?
Yeah, you would still have oscillations with respect to the external magnetic field as well.
Okay,
you would see oscillations in magnetic resistance.
Okay, and the effective doping from the say magnetic field is basically follow the strata or whatever to convert it to actual doping.
That's right.
Okay.
Yeah.
Cool. Thanks.
Yeah, Max again.
Suppose you were in a clean system,
Uh-huh.
like no disorder.
Okay.
Is there something that pins the whole conductance to be 1/2 at this?
Well, I mean, a completely clean Galilean invariant system.
No, not Galilean invariant, but like your Moire system.
Clean, but with Moire, is there something that pins? That's a very good question. I think the answer is no, but I'm not 100% sure.
Yeah, I also don't know.
Yeah, because you still, you still have the scattering off of the periodic potential. Yeah, Dimitri.
So are there also Shubnikov-Tehas oscillations in zero field in addition to Weiss oscillations?
Yes. So in the absence of magnetic field, if you dope, you'll see the Shubnikov-Tehas, and that's the usual Jane sequence, the expected Jane sequence.
And you can extract the effective mass of fermions from this amplitude.
Yeah, that's right.
Okay, thanks.
So you talked about this effective theory, which contains the Moire potential, but I kind of would have thought that, like, if you're on scales large compared with the Moire unison, you don't even need the periodic potential. I mean, like in Fermi liquid theory, you don't write the periodic potential in the low energy effective theory, right?
Right, but I mean, the wavelength of this potential is quite large.
Well, okay, but if you were looking at responses on scales larger than that,
larger than that, you wouldn't see it. That's right.
Maybe you answered this already, but the period you had for these new oscillations, could you just translate that into filling factor?
Yeah, I mean, essentially, this is already written in terms of filling factor. That's why this number is dimensionless. So this is 1 over delta n, where there's the density times Moire unit cell.
So it's at filling factor 0.1?
Yeah.
0.1 and 0.9, something like that.
Something like that. Jetty.
Or maybe it's another conceptual question for me to actually understand what's going on here. Yeah, so for fractional quantum Hall effect, I think we understand the composite fermion quite well, right? The flux basically perfectly screen the charge, and it's no net charge in exact nu equals to 1/2. I'm thinking about in this system, the ferromagnetism states can be very, very different, right?
Sure.
From different twist angle. Is that still apply in this language that the flux attachment actually screen out all the charge, basically?
So
the composite fermion is still charge neutral that is perfectly screened?
You mean in, say, if I have ferromagnetic fluctuations in the problem?
Yes, exactly.
Yeah, so in that situation, well, okay, first of all, I should emphasize that what's not being screened here by the flux attachment is the actual sort of intrinsic magnetic moments. You could sort of roughly think of this more as screening the Berry curvature. But of course, you can ask, okay, what happens if I take this composite Fermi liquid toward the magnetically disordered state? What happens? And that I don't actually quite know the answer to. That's an interesting question. Okay.
Going back to the ED calculations, did you say if you included spin? Was Valley included in those calculations?
Valley and spin are treated the same.
Okay.
Yeah.
So you don't first assume projected?
No, there's just the 1 degree of freedom.
Okay, well, thank you for your talk.
Yeah.